Hello, Trig students. I'm sure you've all been waiting breathlessly for me to get around to making this video, and actually I made it last night, and long story short, something happened with YouTube where it was too long, and I thought it was loading while I was sleeping, and it didn't, so I'm so sorry that we're off to a little bit of a rough start. But we'll make up and get smoother as we go. So we're talking about Chapter 2, trigonometric functions. So recall everything that you've learned about functions from algebra, and that's what a lot of the Chapter 1 review material is about. So I'm going to ask you to do that on your own. And Section 2.1 is about angles and their measure. So there's 5 objectives, and you can find these in the book. The first one is convert between decimals and what we're going to call degrees, minutes, seconds form of measuring angles. So both are used, so we need to know both, and we need to be able to switch back and forth between them. The second one is find the arc length of a circle. Third one is convert between degrees and radians. If you haven't taken trigonometry before, radians may be a new unfamiliar unit of measure that we'll talk lots more about. The fourth one is find the area of a sector of a circle. And we'll talk more about what is a sector of a circle. And the fifth one is find the linear speed. So linear means in a straight line, if you were traveling in a straight line, of an object traveling in circular motion. So it's hard to write very small with the stylus on the tablet, so hopefully you're able to fit everything on your full-size paper there. So there's some introductory material about an angle, and we're going to talk more about that in class tomorrow, so I'm not going to go into big detail here, but we are going to use Greek letters often to represent angles. So this is alpha, beta, gamma, and theta, and when you handwrite them, they look like alpha, beta, gamma, and theta. So work on getting kind of quick at drawing those because we use them a lot. So those are lowercase Greek letters, alpha, beta, gamma, and theta. Our angle measuring convention is going to be that if we start with an angle in what's called standard position, so that means if we put one side of the angle on the positive x-axis horizontally, then wherever the other side of the angle is, we measure counterclockwise and say, how big is that angle? And we'll practice measuring angles tomorrow to get a sense of what is a 30-degree angle? How big is that? So let's talk briefly about quadrants. Hopefully you already know this. So in the x and y coordinate plane, and I'm very picky, and you must label those because we are going to also talk about imaginary numbers, and so you label the axes differently for that. So this is called quadrant 1, where x and y are both positive. Then we have quadrant 2, where x is negative, y is positive. Quadrant 3, where x is negative and y is negative, and quadrant 4, where x is positive, y is negative. This is going to be super important in trigonometry, so if this is a little fuzzy, make sure you review it. So the quadrantal angles are the angles that make the edges of the quadrants. So if you talk about the angle between the positive x-axis and positive y-axis, of course that would be a 90-degree angle. So then if you talk about the angle, it's technically an angle, from the positive x-axis to the negative x-axis, that would be 180 degrees. And of course, if I go all the way around from the positive x-axis to the negative x-axis, that's 270 degrees, and those are considered the quadrantal angles. We could call the positive x-axis 0 degrees just as a starting point. There's 2 common ways of measuring angles, in decimal degrees and in degrees, minutes, seconds, but we'll talk more about that in just a minute. And we'll draw some angles tomorrow so that we can look at how big they are and practice measuring them. So objective 1 says to convert between decimal, so a decimal form looks like 52.46 degrees with a decimal point, and this degrees, minutes, seconds form. So that would look like 52 degrees, maybe 47 minutes and 32 seconds. Those aren't the same, but that's what it looks like when you write an angle in degrees, minutes, seconds format. So one revolution all the way around the circle, well, let's see, we said 90 degrees, 180, 270, must be 360 degrees. And then we use similar to time, where 1 degree equals 60 minutes and 1 minute equals 60 seconds. So just like with time, 60 seconds equals 1 minute and 60 minutes equals 1 degree. So tomorrow we'll practice converting back and forth between decimal degrees and degrees, minutes, seconds form. And we'll be using conversion factors. So if you divide some number by the exact same number, you get 1, right? Doesn't matter what the number is. So if I take 1 degree and divide it by 60 minutes, I must get the number 1. Or if I take 60 minutes and divide it by 1 degree, I must also get the number 1. So these are the conversion factors we'll be using to switch back and forth between degrees and minutes, seconds form. So the next type of measure that we need to talk about are radians, and they're a little tricky at first until you get used to them. So imagine a circle that has a radius of 1. So r equals 1. Well, you know that the circumference of a circle is 2 pi r. So that's how far it is around. Well, this circle, the radius is 1. So for this particular circle, the circumference is 2 pi. Well, if the radius is 1, then the distance that you've traveled around the circle is equal to the size of the angle in radians. So we say there are 2 pi radians in 1 full revolution around the circle. So clearly looking at the picture, this would be pi radians. And then we're going to look at lots of other fractions of radians. So objective 2 is going to be to find the arc length of a circle. And we have a formula, but note this formula says when theta is measured in radians. So theta must be in radians for this formula to work. So S is the arc length. Don't ask me why it's S. I don't know. That doesn't make any sense to me, but that's what everybody uses. So S is arc length. R is the radius of the circle. And then subtended by the central angle theta. So that's saying if you had a circle and you have an angle with size theta measured in radians and the radius is r, that this distance traveled along the circle, the arc length, would be called S, and it would be the length of a piece of string if you were wrapping it around a can of this size. So this is just a formula that you need to memorize. You get to use it a lot in lots of other applications. And so these problems we'll do in class tomorrow, and they're really just plug and chug, plugging numbers into the formulas. Objective 3 is where we're going to convert from degrees to radians, and from radians to degrees. So we need to be able to go back and forth between those two forms smoothly. But I'll tell you that it's a lot like learning a foreign language, where if you're used to thinking in degrees, at first you might have to think in degrees and then translate to radians and then translate back to degrees. But eventually it'd be awesome if you start thinking in radians, because always in calculus, radians are used so that there's no conversion factor necessary. So we have some things that are equivalent when we're talking about the full circle. One full revolution of the circle is 2 pi radians, and that can be important if you're talking about things like wheels spinning, and you say something like 200 RPM. Well, that's revolutions per minute, and revolution is 1 time around the circle. So it's traveled through an angle of 360 degrees, or 2 pi. So if 360 degrees is 2 pi, then 180 degrees must be pi. And if you divide both sides by 180 degrees, you can see that 1 degree must be pi over 180, and 1 radian must be 180 over pi. So we'll practice in class, switching back and forth between degrees and radians. And this is a little table from your book that shows you some of the most commonly used fractions of pi. These are called special angles, and we'll run into them lots more later. So I just want you to see that there's a little table here. You might want to make a flashcard of these if that's a good learning method for you. So number 4 is find the area of a sector of a circle, and a sector is a pi-shaped wedge where you have the center here and the radius, and this is your arc length S, but the sector is talking about the whole area of the pi-shaped piece. So again, theta has to be measured in radians for this formula to work. So we have that the area equals 1/2, r is still the radius, and theta is still the angle between the two sides of the sector of the circle. So this is the angle theta. So again, this is just a formula, plug and chug. So we'll do some of these exercises tomorrow and fill in this blank here. And let's go on to objective 5, which is find the linear speed of an object traveling in circular motion. So if you're moving around a circle of radius r, so the radius is r, and you're going at a constant speed, and suppose s is the distance you've traveled along the circle's edge, then the linear speed, how fast are you running, is called v, and it's going to be s, the distance you traveled over time. Just like you know from algebra, distance equals rate times time, so rate or speed must equal distance over time. So this really isn't something new, we're just talking about it in terms of running around a circle. So this is how fast are you running. Then we have angular speed, and we use the Greek letter omega to talk about angular speed. And again, we have a theta that has to be measured in radians, and we talk about as theta is being swept out. So somebody's standing in the middle of the circle, sighting, looking at the person that's running, and saying, what angle did you turn through? So that's the theta, and this is time. Since the theta needs to be in radians, which are dimensionless, omega has kind of odd units. So it will have units of time to the -1. So it will be like seconds to the -1 or minutes to the -1. So it's going to look kind of strange. So let's see if we can derive the equation that relates linear speed. So we have linear speed is s over t. And angular speed is theta over t. Let's see, we learned an equation earlier that said s equals r theta, where s is the arc length. So v must equal r theta over t. Well, if v is r theta over t and omega is theta over t, can you see how they're related to each other? Where v over r equals omega. So this is another important equation that relates the linear speed to the angular speed. And we'll talk lots more about that, and we'll work on this application problem in class tomorrow. So hopefully this is less than 15 minutes this time, and so the video is going to work. Sorry about the delay.